So here we have a question on circular motion, which is basically targeted for JEE mains. A particle P of mass m is attached to a vertical rod with two identical strings AP and BP of equal length. So these two strings are of same length, and the distance between these support points A and B is also equal to L. The setup is rotated about AB with an angular velocity omega as shown, and gravity is acting vertically downwards. So first we need to find the value of omega for which the particle remains at position B. So this particle P will remain at this lowest position B. Second, we need to find the range of omega for which the tension in the string AP is greater than mg, but the other string remains slack. And the third part is to find the value of omega for which tension in the string AP is twice that in the string BP. So let us see the solutions part by part. In first part, the particle has to remain at position B. So definitely this string BP is slack and the tension T2 will be remaining 0. So the tension T2, I will consider tension T2 in the string BP and tension T1 in the string AP. So if the particle remains at position B, it means the tension T2 is 0. The string BP is slack. So only force that will be acting on particle will be the tension T1 and the weight mg, right? So it is if it is not moving in the vertical direction, then I can say that T1 cos theta is going to be mg, and T1 sin theta will be providing the centripetal acceleration to the particle. So T1 sin theta will be m omega square into this radius. This will be the radius of the particle. If this point is m, then mp, this distance is the radius of the circular motion in which particle is moving. So if the AP length is L and this angle is theta, then the radius of circular motion will be simply L sin theta, right? So tension T1 will be m omega square into radius of the circle, that is L sin theta. So this sin theta term gets cancelled out and tension T1 will be m omega square L. So if I replace the value of tension T1 in this expression, then cos theta will be mg by m omega square L. And since cos theta is less than 1, cos theta is to be less than 1. So the value of omega is greater than under root of g by L. So if the aim is to keep the particle at this position B, it means the value of omega has to be less than this value under root of g by L. If the value of omega remains less than under root of g by L, then there will be no circular motion of this particle and the particle will remain at position B. So the answer of this part, the first part, the answer of this first part should be omega less than under root of g by L. If omega remains less than under root of g by L, then the particle will not undergo circular motion and it will remain at this position B, the lowest position. Okay, so the second part is that the string BP has to remain slack, and one more condition is required, that the tension in this string should be greater than the weight of the particle mg. So from this expression, we had calculated from this first expression, T1 cos theta was equal to mg. So T1 is mg by cos theta. We need the value of tension T1 to be greater than mg. So cos theta has to be less than 1 or theta has to be greater than 0, right? And also if the string BP remains slack, it means that the angle theta that the string AP is making from the vertical, if this angle remains less than or equal to 60, equal to 60 is the critical case. So if this angle theta remains less than 60 degree, then definitely the string BP is remaining slack. Right. So the first condition is theta is greater than 0, and our next condition comes out to be that theta is to be less than 60. I'm taking this equality for the critical condition. So the range of theta is from 0 to 60 degree. So the range of cos theta is going to be from half to 1. Now again the value of cos theta we calculated in the first part, g by omega square L. So g by omega square L, this term has to be greater than half and less than 1. So we get a range of omega which is greater than equal to under root g by L and less than under root of 2g by L. So if omega remains in this range, then in that case we will get the tension T1 to be greater than mg and the string BP will remain slack. So this was our second part of the question. In the third part, we are asked that what should be the value of omega for which tension T1 is twice of tension T2. So if I take the tension T2 as T, then the tension T1 is 2T. Now simply the particle is not moving in the vertical direction, so I'm equating the force in the vertical direction. Net force has to be 0. So in vertical, 2T cos theta should be balanced by mg plus 2T, sorry, plus T cos theta. So 2T cos theta is equal to mg plus T cos theta. So I get the value of T cos theta to be mg. This is our first expression. And the sine components of these tensions will be providing the centripetal acceleration. So 2T sine theta plus T sine theta will be equal to m omega square into radius is going to be L sine theta. So the value of 3T comes out to be m omega square L. So I'm replacing the value of tension T from this first expression, which is mg by cos theta. So 3 mg by cos theta is m omega square L. Now, since this radius, you can see that this angle is theta, this length AP is L. And this point, if this is point M, this AM distance will be L by 2. Okay, this distance will be L by 2 and this distance will also be L by 2 because the string BP is not slack. So if this string BP is not slack, in that case, this triangle will be an equilateral triangle, right? So from this triangle AMP, I can say that the value of cos theta is half. So if I replace the value of cos theta is half in this expression, I'll get the value of omega to be under root of 6G by L. So for this particular value of omega, tension in string BP will be T and the tension in string AP will be twice of that in the lower string.